This program is going to explore radicals. A radical is a species with an unpaired electron. That unpaired electron makes it very reactive. Sometimes radicals are referred to as species with a dangling covalent bond. Let's look at how they're created. One method to create them is to break a bond between two halogens. In that case, the bond, when it breaks, one electron moves to each of the bromines, creating the bromine radicals that you can see here on the right-hand side. I can also represent this in a more symbolic form, where I take a dashed line to represent the pair of electrons, and using a single harpooned arrow, one electron moves to the right and the other to the left. And there you see on the right the symbol for a bromine radical, simply a bromine with a dot to it. This is called an atomic radical because it's based on an atom. We can also get radicals in other forms. This splitting is sometimes referred to as homolytic fission, homo meaning same, lytic breaking. So let's take a look at this happening in another situation. Here I have bromomethane, and I'm going to use a single harpooned arrow to represent one of the electrons in the bond moving towards the bromine and the other remaining with the carbon. As a result now, I've created a molecular radical, a molecule which has one unpaired electron. At this point, I want to introduce what would happen during what's called heterolytic fission, where we don't get the same splitting. I'll take the same bromomethane and break it this time using heterolytic fission. In this case, I'm using a two harpooned arrow to indicate that both electrons move over towards the bromine. As a result, the bromine now has an extra electron, causing it to form the bromine ion with a -1 charge. Carbon, who's lost an electron, now becomes positive. So heterolytic fission indicates the two electrons moving in one direction, whereas homolytic fission indicates one electron moving towards each of the atoms. Ionic radicals can also occur, where we have ions forming radicals. Here's the formula for one, and let's look at its Lewis structure. Because it's an ion, I have to put it in square brackets, and the positive sign designating its charge. Here you can see between the carbon and the hydrogen, one unpaired electron. This species can be created in something called mass spectroscopy, which you'll learn about later on. Here's an example of a species with a negative charge creating a radical. This is called the superoxide radical and is found in many metabolic pathways, particularly involving the mitochondria. And here we can see its formula. Again, we're using square brackets to indicate it's an ion, and we can notice here the one unpaired electron. Let's look at a couple of questions that involve radicals. First of all, we're going to draw the Lewis diagram for the hydroxide ion and compare it to the hydroxyl radical. First of all, the hydroxide ion will have 8 pairs of electrons. So you'll see those located around the oxygen. It also has a negative charge, so I have to put it in square brackets and indicate that negative charge. Now we'll look at the hydroxyl radical. I don't use square brackets because the radical does not have a charge, but it does have an unpaired electron. In fact, one less than in the hydroxide ion. Which of the following is likely to form a radical? One of the key features of the radical is the unpaired electrons. Therefore, we should have an odd number of electrons when we total up the number of electrons available for our Lewis diagram. So in our first case, H2O, the two hydrogens give one valence electron, the oxygen 6, 8. So that's not a likely candidate. My next, ethane, again, 4 plus 4 plus 6 gives me 14 electrons. Again, not a likely candidate. Nitrogen dioxide, however, has 5 plus the 2 oxygens at 12, gives me 17. This is a likely candidate then to have an unpaired electron. And just to show, the last one also has an even number. Again, the 2 oxygens plus 2 extra because of the -2 charge. I hope you found that useful. Questions are always welcome.